All right, so welcome to our last class of May, believe it or not. And today's plan, we're going to continue solving triangles. We're going to look at the other cases that we weren't able to address last time, the side, 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 and the side angle side. And then I'm also going to show you some other ways of getting areas of triangles that kind of correspond to these other things. But to get those new cases, we have to develop a new law, and it's called the Law of Cosines. And so that's what we're going to build today and then use it. But before I go there, I'll turn it over to you guys. Any questions on the homework or anything else you'd like to ask about before we get going? All right, well, I'm not hearing anything and I'm not seeing anything. So I'm going to go ahead and hop up to the whiteboard and I will be back with you in just one moment. All right, so we're in the process of solving triangles, right? Given some information, finding out the rest of the triangle. And we've been dealing with triangles that are not right triangles, right? Complete triangle. And trying to find out how we're going to go about it. And we always need three pieces of information. And so we kind of made a list last time of the different sets of information that we could use, right? Three sides, two sides and an angle, two angles and a side. And last time we developed the law of sines, which took care of the two angles, the two angles cases, and one of the two sides cases. But we need a new law to actually get the other ones. And this one's called the law of cosines. So let's build this guy, and then I'll show you how we use it. So I'll start with my nice generic triangle, kind of like we did before. And let me just label some angles here. I'm going to call this one, let's say, alpha. This one will be beta, and this one is gamma again. Which with my naming scheme means that my sides are going to be A, B, and C here. Remember, I always go with the English alphabet letter opposite the Greek alphabet letter of the same type. So A goes with alpha, B goes with beta, and C goes with gamma as opposite pairs. All right, so we're actually going to do something very similar to what we did last time when we built the law of sines. We're going to start by dropping in a perpendicular here. So this is a right triangle. But this time, instead of looking at the sines of these angles, we're going to look at the cosines of these angles. So for example, let's look at alpha. Now, alpha is part of a smaller triangle. Let me kind of highlight it here in purple. And if I want to know the cosine of alpha, I need to know this adjacent side. But this purple length, I don't know what it is. I know the entire length of this is C, but I don't have the entire length. I only have a portion of it. So what I'm going to do for right now is I'm just going to call that X. It's some unknown length. I'm just going to call it X. But if I have that, then I know that the cosine of alpha is going to equal X over B. Okay, so if I know that X, there's my cosine of alpha. Now I want to do something similar with the beta, but I'm going to be in a different triangle over here. Let me kind of draw it with this sort of maroonish bit. And if I were to look at the cosine of beta, I would do the same kind of thing, but I would need to know this length, this bottom length, which again, I don't know. But what I can do is I can actually call it C minus X. So this length right here is c minus x. And hopefully you can see why that would be. If this purple length is x, this remaining piece is going to be c minus x. It's going to be the bottom taking away my purple length. So this is the relationship between the alpha and the beta and their cosines, right? So again, it's the good old adjacent over hypotenuse. All right, so now what we need to do is a little bit of algebra that we're going to get with the Pythagorean theorem. So this vertical side, let me call that h again, kind of like we've seen before. And here's what we know about how h fits into everything. In the purple triangle, we get that h squared plus x squared is equal to b squared. Right? So that's from that triangle right there. And then from the other right triangle, we get that h squared plus c minus x squared is equal to a squared. It's exactly the same idea, Pythagorean theorem on that one. So here's what we're going to do. We're going to just play around with these equations and do a little bit of algebra, turn it into a little bit nicer form. So the first thing I'm going to do is eliminate my h. Because from this, I get h squared is equal to b squared minus x squared. So let's just take that and fire that in here. All right, so that's one less letter, one less piece of information that we just can get rid of. So we've got now b squared minus x squared plus, the other thing I'm going to do is I'm going to FOIL this out. So I get c squared minus 2cx plus x squared. So some good news, the x's here, this x squared and this x squared, go away. So once that's gone, I'm going to just switch sides real quick here. So we get a squared is equal to b squared plus c squared minus 2cx. So almost everything is gone, right? There's just very little bit left in here. I mean, we got our a, b, and c. We got our three sides. But let's get rid of this x right here. Now, to get rid of that x, we're going to come back to this first cosine, because I can multiply both sides of that by b to get x equals b times cosine of alpha. So I'm going to put that in here. So that this turns into a squared equals b squared plus c squared minus 2bc cosine of alpha. And again, just in case you didn't follow what I said, let me show you. This becomes x equals b cosine alpha. And then I took that, fired it in here. Okay, so this is the ultimate algebra, just plug stuff in, get rid of other things. All right, well, this is when I have to say, ta-da. All right, that's your cue that we're done. We're done. This is the law of cosines. So let me, I'm going to copy it up here so we always keep it. I won't erase it if I write it up here. And what we got for the law of cosines is that a squared is equal to b squared plus c squared minus 2bc cosine of alpha. So notice what this has. That's a little bit different than the law of sines. The law of sines, we always had two angles in there and two sides. This one has all three sides, A, B, and C are just the sides, lengths of the sides, and then one of the angles. So it's a tool that's going to allow us to use different information, but it's still a relationship that's going to always hold for every triangle, right? Because we did this for a generic triangle. I didn't say this triangle had to be anything special. This is going to hold. Now, what you're going to see when you see the law of cosines is two more lines on this. They'll give you two other options. And those two other options would come from dropping perpendiculars to the other sides. But they have very similar forms. The next one is b squared equals a squared plus c squared minus 2ac times the cosine of beta. And then the last one is c squared equals a squared plus b squared minus 2ab cosine of gamma. So really, it's just we're changing the names on things, but it's always the same form. So let's put a box around that, because this is what we're going to reference, and this is what we're going to use when we're dealing with the other two cases, when we're dealing with side angle side and side side side. All right, so before we actually dive in and do some examples, any question about this derivation? It's a lot of geometry and a lot of algebra. Brings us to this spot. Okay, so let me actually show you how we use this in the other scenarios. So I'm going to go to side angle side. Let's do this one next. So this is the second case where we know two sides. It's just this time we're going to know an angle that's in between them. Right? When we did it before where we had two sides, the angle was opposite one of the sides. And in that case, we used the law of sines. This time we're going to have an angle that's between the two sides. So here you go. Here's a generic triangle. And let's say that we know that this length down here is 10. This length is 7. And let's say that we know that the angle in between them here is 37 degrees. So this is an example of side angle side. We know a side, then an angle, then a side. So first, you should be able to see here why we can't use the law of sines. Because the law of sines that we developed last time required knowing a side and an angle that are opposite pairs. And we don't have that. The only angle we know is opposite an unknown side. And there's no other way that we can get any of these two angles because we don't have any other information. So the law of sines is out, but the law of cosines is totally going to work. So let me just label some things so that we can find the information that we need. So I'm going to go ahead and just call this missing side A for the sake of having a letter, which means 37 degrees is our alpha. So the other two can be whatever angles we want, but I'll go ahead and kind of label them like we did before, beta and gamma in this order. So to solve this triangle, we're going to need A equals, beta equals, and gamma equals. All right, so the first step is going to be using the law of cosines to find the third side. All right, so when you're in side angle side, find the third side first. All right. So this is one of those things where there's not an option, like this is the first thing that you do. We're going to find the third side. So we're going to find A, which means we're going to use the first form of the law of cosines, the first one that's written there. So notice, to do this, we need to know B and C, Well, we got those. Those are these two sides. And then we also need to know alpha. Well, we do know alpha. That's the angle that was given to us. All right, so if we do that here, we're going to get a squared equals 7 squared plus 10 squared minus 2 times 7 times 10 times the cosine of 37 degrees. So we've got everything, right? We've got everything here. And now we can jump to our calculator to figure out what this value is. All right, so go ahead and put this stuff into your calculator. As always, I'm going to warn you, make sure that you are in the correct mode. Make sure that your calculator is going to calculate this with degrees and not radians. Right? So just make sure you're in the right mode. But you do this computation and you get a value of 6.098. Right, so A is approximately 6.098. Now I'll just round it to the nearest 10. Let's call it 6.1. All right, so there you go. We just found a side. Cool. So now we've got all three sides. We have to go and find another angle. Now we have a couple of options of how we're going to do this. Now that we're at this point, we can use law of cosines again. Pick one of the different angles, like let's say we're going to go beta. And we could use law of sines here or cosines here because we know all of A, B, and C. So we can put all those in. Or we can use the law of sines because now we do have a side angle pair, right? We know that this side is now 6.1. So we got a side angle pair, we can use law of sine. So it's totally up to you. You can pick which way you want to do it. All right, but the second step here is going to be find a second angle. And you have some options. Like not only do you have options of whether to use law of sines or law of cosines, but you also have options of which of the angles you want to find. Okay, now I have a recommendation for you. I have a suggestion on which angle you should find and which method you should use. If you don't want to follow this way, it's totally fine. It's up to you. This is what I do. I think it's actually easier, but it's totally up to you. So what I do when I want to find that second angle, I find the smallest remaining angle using the law of sines. All right, so this is Bruce's choice. And I legit mean that it's totally your decision if you want to do this or not. I know that there are some teachers that are like, you got to do it my way. I'm not that guy. Right? I want you to do it right. But there are lots of correct ways to get here. So if you don't want to do it this way, that's totally fine. But this is what I do. I look at these angles and I figure out which one's smaller. Ooh, do you remember how to tell? How do you tell if a side is small or an angle is smaller than the other angle?
By the length of the opposite side.
Yeah, perfect. You look at the opposite sides, and we saw that the longest opposite side has the largest angle, and the shortest opposite side has the shortest angle, right? So that's how I'm going to recognize that. And then I'm going to use the law of sine. So this is how this one would play out. All right, we already got our A. Let me bring this up a little space here. So the smallest remaining angle is going to be beta. Right? The shortest side is A. The next shortest side is B. So I'm going to find beta. So we'll jump to the sine of beta over b business here. So I have sine of beta over b is equal to, and then I need to go to the angle that I actually know. I got the angle side pair of A. So sine of beta then is going to equal 7 times the sine of 37 degrees divided by 6.1. So I'm going to jump to my calculator. I'm going to do inverse sine. All right, that's how you get from sine of beta to beta. So I'm going to do inverse sine of all that garbage. So I get inverse sine of 7 sine of 37 divided by that 6.098 blah blah blah. Right, 6.1. And what I get is 43.7 degrees. All right, so I'm going to put that in here for my beta. It's 43.7. All right, so hopefully you guys agree that that's a pretty fast way to get an angle. I'll explain why I specifically chose the smallest remaining angle in a second. But there's my beta, 43.7 degrees. But now that I have a second angle, I can get my third angle. And this one, I'm not going to use law of cosines, I'm not going to use law of sines. I'm just going to use the fact that these angles, these three, all add up to 180. And so I take my 180, I subtract 37, I subtract 43.1, or sorry, 43.7. And you should get 99.3, I believe, for this one.
How did you get 43.7 in your calculator? Because I'm just not getting the same answer.
Okay, so I did inverse sine of 7 sine of 37 over 61, or sorry, 6.1. And if you did this, but got a different number, a couple of things to check. One, make sure that you're in degree mode. Because if you're not in degree mode, it's going to think that's 37 radians, which is a very different angle. Okay. But if you're in degree mode and you still didn't get this, then it's going to most likely be an order of operations thing. You need to put in some parentheses to, to do your, make sure that all of this is inside the inverse sine. Because on some calculators, if you just typed it in, you'd get inverse sine of 7. And then times sine of 37, and then divided by 6.1, which will be a very different number as well. So I don't know. That was you, Danielle, right? Did you figure out what you did?
Yeah, I got it now. Thank you.
Okay, cool. All right, so in the side angle side case, it's a very clear, here's what you do. First, find the third side using law of cosines, then find a second angle. So let me get back to that second angle and why this is my choice. First of all, I just like the law of sines a little bit better than the law of cosines because it's not as ugly and it's not as messy and it's a lot easier to solve, right? And when you just have one fraction equaling another fraction, that's quick. Think about having to take one of these and solving, say, for beta. You have to move the a squared and the c squared over, and then you're going to have to divide by minus 2ac, and then you're going to have to take an inverse cosine. And there are a lot more steps. So the fewer steps, the less likely I'm going to make a mistake. So that's why I picked the law of sines. But now, the reason that I picked the smallest angle is because of that situation that we ran into when we were doing the side angle case. That was the one last time, that was the ambiguous case. And remember how that sometimes led to two triangles? and sometimes 0. When you do inverse sine, there's also the other possible angle. You can also get 180 minus whatever angle we just found. Like that's another one that actually works with sine. But if I choose the smaller remaining angle, I know the other one's not an option. Because think about what I get. Like if I take this away from 180, I get 136 or something like that. That's going to be the biggest angle if I have an angle of 136 degrees. But by choosing one that I know can't be the biggest angle, I don't have to worry about it. Okay, so this is some, I said this is just advice, whatever. This is actually the really strong advice. Mostly if you don't want to have to check other angles, if you want to just be able to accept the number that came out of this and just go, oh, my calculator gave me a number, I'm writing it down, because that's our instinct. If you want that to be the case and to never run into a problem, always pick the smaller remaining angle. Because here's the deal. Let me show you what would have happened if instead we had gone for gamma. All right, so we know that beta is equal to 43.7. But if I had done this for gamma, so we have sine of gamma over 10 is equal to sine of 37 over 6.1. And so you do the same thing with your inverse sine. Let me actually just do it real quickly here. We're going to get 10 sine of 37 divided by that 6.1. All right, I got an angle of 80.7 degrees. And if you look at what we actually found for our triangle, we found that gamma was 99.3, not 80.7. Well, that's because another angle that also works is 99.3. And we wouldn't have known. We wouldn't have caught that. We probably would have just put this in our box around it and then gotten a wrong value for beta. Okay, so if you do this, go for the smaller, because if you go for the bigger, you can run into the problem of the, yeah, but there's also the or. And me being the lazy mathematician that I am, I don't want to add to my workload. Having to think about the or and check that other one out. No. I want just, here is the answer. If you do it this way, you will get the answer. You don't have to worry about the or, and it's going to save you time. It's going to definitely save you heartache, right? Nobody likes getting that red X of shame on the homework. Nobody likes losing points on their quizzes or exams. So go for the smaller remaining side. And in general, if you have an option with sine, with law of sines, go with the smaller side. Go with the smaller angle. It's going to make it less likely that you run into a problem. All right, so there's an example of the side angle side case, and they're all the same. They're absolutely all the same. You just might use a different one of these, even though they're all the same form. You just find the side that you're missing, and then go to your angle. All right, so how are we feeling about that? Is it not too bad? Side angle side. All right, so let's go to the side case. So this is going to be where you actually just know all three sides. And in a lot of applied situations, real world situations, this is where we are. It's a lot easier to measure sides than angles, just physically, right? I can just go take a measuring tape and measure out distances and get my lengths. I need special tools to find angles. So this is actually one of the more common things that we'll see. But let's just say, here's our generic triangle. And let's say that we know the side lengths are 11, 7, and 5. So I want to solve this triangle, which means really I'm just looking for angles. So we'll go ahead and label them exactly the same way we did before, alpha, beta, gamma. So here's our list. We just need to find those 3 angles. All right. So again, we cannot use the law of sines. Law of sines will not work. Because for the law of sines, you need to have side angle pair. Well, we have no angles, so law of sines. So let's think about law of cosines. If we look at the law of cosines, just again, look at the first one. What you'll see is that it involves all 3 sides and 1 angle. Well, if we know all 3 sides, we know A, B, and C, the only unknown is alpha. And for the second one, the only unknown is beta. The third one, the only unknown is gamma. So either, with any of those 3 forms, we can use that to find an angle. All right, so we're going to find an angle first. And for this one, I'm going to suggest that you find the largest angle first. And we're going to do this using the law of cosine. So with law of sines, I suggested going with the small angle, but law of cosines, I'm going to suggest you go with the biggest. And here's why. Think about inverse cosine. Inverse cosine brings you angles between 0 and pi, or between 0 and 180 degrees. All of those are angles that are in a triangle, and you don't have to worry about or with those. So if this one catches a big angle, awesome. That angle is over 90 degrees or whatever. We're never going to have to worry about the or ever again. Okay, so when you have a choice with law of sines, go small. Law of cosines, go big. Okay. So law of sines, go small. Law of cosines, go big. All right, so which of these is going to be biggest? Alpha, beta, or gamma?
Gamma.
Okay, it's going to be the gamma because it's opposite the longest side. So find the longest side, go opposite it. So we're going to find gamma. So we're going to use this third form of the law of cosines. So we've got c squared equals a squared plus b squared minus 2ab cosine of gamma. I'm going to rewrite this real quick. I'm going to solve it for cosine of gamma. So just a little bit of algebra here before I plug in numbers. I've got that the cosine of gamma is going to be a squared plus b squared minus c squared over 2ab. So let me put in those numbers. So a was 7, so 7 squared, b was 5, and c was 11. So 7 squared plus 5 squared minus 11 squared over 2 times a times b, so 2 times 7 times 5. So this one we're going to do inverse cosine. So we'll do inverse cosine of all that stuff inside. Again, I'm going to warn you the same warnings that I gave you before. Make sure that you're in the right mode. Okay, make sure you're in the degree mode here since we're going for degrees. And also watch your order of operations. But what I got when I did this was that gamma is equal to 132 point, I'll round it to the nearest tenth again, 132.2 degrees. All right, so law of cosines got us an angle. So it's a bit more work to get the angle using law of cosines. But in this situation, side, 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 we don't have a choice. That's the only way we can get an angle. All right, so now we got to find a second angle. But this is where we have options again. We can use law of cosines, pick a different one of these and find a different angle. Or we can use law of sines, because now we do have a side angle pair. And that's actually what I do. So this is going to be, again, Bruce's suggestion, is then find the smallest angle using the law of sines. So just like gamma was largest, we know beta is going to be smallest because beta is opposite the shortest side. So I'm going to do sine of beta over b is equal to sine of gamma over c. So sine of beta is going to equal 5 times the sine of 132.2 divided by 11. So we can use the inverse sine here. And once I do that, make sure my parentheses are all good. I get 19.7 degrees if I round it to the nearest 10. All right, so beta is 19.7. All right, well, there you go. There's the smallest angle, and I definitely don't have to worry about the or, right? Because the or is going to be much bigger than 132.2, and I know it doesn't even, that can't be. All right, so then I'm left to get alpha, but let's, this is easy now. 180 minus 19.7 minus 32.2. And I believe that's 28.1 degrees. And there you go. We have now solved this guy, given all three sides. So again, very systematic, very just do the process. And unlike the ones that involve law of sines, we don't have to worry about anything. Law of cosines, just it is. You get the answer. There's never an or, there's never an ambiguous case. Right? That just doesn't happen. But I will tell you that with side, 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 sometimes you're given three sides that will not form a triangle. That can happen, right? Like what if I told you the three side lengths were 1, 2, and 500? there's no way we're going to make a triangle that works that way. And we don't even have to go to 500. What if I just made it 5? What if I told you the 3 lengths were 1, 2, and 5? So you go, all right, so here's my one that's of length 5. And then I'm going to have something that's length 1 and another one that's length 2. It's never going to happen. So it is possible that if someone says, hey, find, solve a triangle with these given sides, that it doesn't actually form a triangle. In terms of how are you going to know? First of all, if you just jump to the law of cosines, you're going to get an error here when you try to get the angle, because your cosine value is going to be bigger than 1 or smaller than -1. Okay, so it'll get caught there. But a real easy check, given 3 sides, to see if it can form a triangle, is that if you add up any 2 of them, it has to be bigger than the third, right? Like, look at this set here. You've got 5 and 7. Well, 5 plus 7 is 12. It's bigger than 11. 11 plus 7 is 18, which is bigger than 5. 5 plus 11 is 16, which is bigger than 7. We call that the triangle inequality. That's the fancy name for it, because it's an inequality that comes from triangles. But it's the sum of 2 sides has to be greater than the third. So that's the way you would catch something like the 1, 2, and 5. 1 plus 2 is not bigger than 5, so it can't form that triangle. But like I said, even if you don't notice that at the start, you'll catch it in here. When you go to do inverse cosine, your calculator is going to give you, it's going to yell at you. It's going to say undefined, non-real result, error. No, I mean, who knows what your calculator actually says, but it will let you know, it will make you aware that there's an issue. And in that case, it's there is no triangle because those sides aren't big. All right, well, hey, you guys now have all the tools you need to solve any triangle. Any of them. It doesn't matter. You can use law of sines and law of cosines, and you're going to be good to go. And in fact, remember how when we were doing the right triangle stuff and we saw that you could do different things using the trig functions and all that? Turns out you can still use the law of sines and the law of cosines on these. You don't think about doing it that way, but it totally works. Like, check this out. Let me give you a right triangle, and let me show you how the law of sines and the law of cosines is actually in there. So, for example, let's look at this right triangle, that guy, and I'm just going to give you 2 sides. So let's say that this is 1 and this is 4. And I said solve it. So what's the first thing you're going to do? If this was on an exam, what's the first thing you're going to do to solve this?
Find the length of the adjacent side and then the angles on the inside.
Yeah, so I would definitely do that. All right, what about this guy right here? Call it A. And the way you would do it is with the Pythagorean theorem, right? You'd have a squared plus 1 squared equals 4 squared. Well, instead, let me show you how we would use the law of cosines. So if this is A, then the side opposite is going to be alpha. We'll make this one beta. So think about finding A from the law of cosines. Well, we know gamma, and we know B and C. And we're trying to find A. So let's look at this guy right here. We're going to get C squared equals A squared plus B squared minus 2AB cosine of gamma. Real quick, gamma is 90 degrees. also known as pi over 2. What's the cosine of 90 degrees? Or the cosine of pi over 2?
Isn't it 0?
0.
It is 0. So this is going to be 0 times 2ab, so that stuff goes away. And what we're left with is c squared equals a squared plus b squared. And that should look familiar. That's the Pythagorean theorem. So check this out. The Pythagorean theorem is just a special case of the law of cosines. It's the law of cosines when one of the angles is 90 degrees. I know that none of you found that as interesting as I find that, but that's kind of cool. So when you do the Pythagorean theorem, guess what? You're doing the law of cosines. You just didn't know it. All right, so that's where the law of cosines thing comes in. Now, suppose we wanted to find an angle, right? Well, let's say we're going to try to find b using the law of cosines, or beta from the law of cosines. So we're going to go sine of beta over b is going to equal sine of gamma over c, because those we know. So we're going to get sine of beta is equal to b times the sine of 90 degrees over c. Well, just like before, we know this, sine of 90 degrees or sine of pi over 2. That guy equals 1. So this tells me that the sine of beta is equal to b over c. Okay, well, b, that's the side that's opposite beta because of our naming scheme. And then c, that's the angle opposite the right angle, which is the hypotenuse. Hey, guess what? Sine is opposite over hypotenuse. So, Katoa, right? So check that out. When you did just the good old sine is opposite over hypotenuse, that was the law of sines, where we're in a right triangle. So you've been doing law of sines and law of cosines for a long time. You just didn't know it. And now we're able to extend it to other kinds of triangles that are not right. Anyway. All right, so law of sines, law of cosines, those are your friends, right? Get used to using them. They're very procedural. It's the same thing every time. So once you, these are the kinds of things that when you practice them, you get really good because it's the same process over and over and over. You develop the mental muscle memory kind of idea. All right, so in terms of side lengths and angles, you're now good. You can find any of them for any triangle. But you may remember, and you may not, because this was way back in like the very beginning of April. The very first day when I said, hey, trigonometry is triangle measurement. And I asked you guys, what are some things that you might want to measure in a triangle? Obviously on that list were the lengths of sides, the angles. But another big one that was on there was area. And some of you brought that up and said, well, how about the area of triangles? So let's look at the area of triangles. And let's see if we can figure out different ways that we can actually calculate its area. So I'm going to ask you, because I know you guys know this, give me a formula for the area of a triangle.
One half base times height.
Beauty. 1/2 base times height. That's the one that everybody remembers. And this is the one that you were taught probably first. You get 1/2 base times height. So if this is my generic triangle, the base is this side, and the height is this length of a perpendicular that's coming down. And we know that the area is 1/2 base times height. So am I correct? Everybody knew this one, seen this one. How about this? Do you know where it comes from? Do you know why that formula works? Have you even wondered? See, I'm that guy. I'm that guy that like you tell me something and I immediately go, is that true? Why is that true? Like I am so skeptical of other people. I'm all about no, I got to convince myself that it's actually right. I think that's why I'm good at math is because I'm presented with something and I will like grind it into the dirt until I know for sure that it works. But I always was curious. I was like, where did this come from? And I do remember asking my teacher forever ago. I mean, I don't know when I first learned this, but it would have been a long time ago, right? And it was kind of cool because she was like, well, it's really kind of easy. She said, imagine you just extend this out, make a copy of, say, this little triangle that's on the right. And we're going to make a copy of the triangle that's on the left. Because we know that those triangles are going to have the same areas. She said, note what kind of form, what kind of shape do you get if you put these together? And me being me and you guys being you, probably gonna go, well, yeah, it's a rectangle. Okay, well, what's the area of a rectangle? Well, it's the length times width or base times height or whatever. Okay, so the area of the rectangle would be base times height, but our triangle is only half of it. It's like, oh, cool. All right, so that's where that actually comes from. It's 1/2 base times height. Now, that formula is awesome. It's super, super useful. Like you can plug stuff in, we can get our area. But there is a bit of a problem with it. And the problem with it is you need to know what that H is. And that H, you're not always given. Right? It's not always something that we measure. Because really, if you think about it, what do we measure in the triangles? Well, it's the side lengths and it's the angles. So what we're going to do here is we're going to actually create 2 other area formulas that get us away from having to know this guy H. It gets us back to just knowing sides and angles. Okay, so let me just redraw this picture. But we're not going to have our craziness here. But let's just put in the A, B, and C. All right, so I want to be able to figure out the area knowing the side lengths or possibly the angles. All right, so there's our alpha, that guy's gamma, and this one's beta. So given this, can we get the area? Now, I am going to do what we've done before, which is just put in this perpendicular and call it H, but I'm not going to actually calculate it. Instead, I want to substitute it in. I want to get some other relationship with H. And so here's what I'm going to do. I'm going to look at this triangle right here. And thinking about H, what I know is that the sine of gamma is equal to H over A. Because it's the opposite side over the hypotenuse in this smaller blue right triangle. So H is equal to A sine of gamma. So let's take this and fire it in there for the H. So we're going to get area equals 1/2 B times A times sine of gamma. And notice how this has nothing to do with H and has only to do with sides and angles. So I'm going to rewrite this down here and we're going to put a box around it. But I'm also going to change the angle name. And I'm doing this just to make it so that, because this is what you'll normally see in a book. I want it to be just familiar. but it's A equals 1/2 AB sine theta. So A and B are two sides, of course, and then theta is just the angle in between them. So if you know two sides and an angle in between them, so side, angle, side, you can actually get the area of the triangle. So learn this one. This is going to come back. We use this all the time. 1/2 AB sine theta. But that's your area.
So would my theta be C in this equation?
It'd be your theta is gamma. Theta is the same angle as gamma.
So if I did like 1/2 AC sine of angle B, then
Okay, yeah. So you can do this with any of them. My recommendation is don't get hung up on the names. And when I say names, I mean the letter names for angles and all that. Think of it this way: you need two sides and the angle in between them. So it'd be 1/2 AC sine beta, 1/2 BC sine alpha, 1/2 AB sine gamma. So I think my answer to your question is yes, it would be 1/2 AC sine beta if those were the sides and the angle that you knew. Did I answer your question or did I just confuse it?
yeah, I was kind of just manipulating it for if I had different numbers and sides and angles.
Yeah, so really what it comes down to, like, here you go. This would be an example. Let's find the area of this where I've got lengths 4 and 5, and this angle is 13 degrees. Okay, so the area is going to be 1/2 times 4 times 5 times sine of 13. That's it. And notice how I didn't name them. I didn't go, oh, okay, I'm going to call this guy A and this guy. No, I don't do that. That's too much work.
So it's just based off the relationship of having two sides with an angle in the middle.
Yep. A and B are any two sides. Theta is the angle in between them. That's all you need in order to find the area of a triangle. Is two sides and an angle in between. Now, if you're not given that information at the start, because like this is a side angle side situation, but let's say we were in one of the other scenarios, an angle side. Well, just keep solving your triangle until you get to two sides with an angle in between them. Right? If you had three sides, like I told you, okay, the lengths here are 4, 5, and 7, but no angle. Find an angle using the law of cosines. Then use that angle in the two sides that are on both sides of it. So it's always any two sides and the angle in between them. You'll just see it always written as 1/2 AB sine theta. That's why I wanted you to see it this way, because I'm always going to say it that way, because that's all you'll ever see going forward. But don't get hung up on the names. It's two sides and the angle in between them. That's it. So I like this area formula a lot. I use it a lot. In fact, I use it way more than 1/2 base times height. In fact, I can't tell you the last time I actually used 1/2 base times height. It was probably sometime when I was teaching a class where it came up, like in trig or something. But when I'm actually doing this for other stuff, primarily in the calculus world, or when you deal with vectors, you do this a lot. So you'll see this other places, like in physics. I always do 1/2 AB sine theta. That's my go-to. Okay, so there's area formula number 2. Right, the first one, the 1/2 AB or 1/2 base times height, you've known forever. Here's your first new one, but it's pretty useful. Now, the third one I'm going to show you, I'm not actually going to prove it to you because the proof is kind of long and boring, and I know that at this point you guys don't care. So I'm just going to give it to you. If you are curious where it comes from, I'll be happy to sometime during office hours stop by and I'll show you. But this is called Hero's formula. Also, sometimes you'll see it written as Heron's formula. Guy goes by a couple of different names. I like Hero's. So Hero's formula. Now, this one allows you to get the area if you know all 3 sides. Now, what this formula looks like, I'll explain what it is in a second. But in here you have S times S minus A times S minus B times S minus C. So A, B, and C, those are the 3 sides of the triangle, like you're used to. But then the question is, what is this guy S? Well, S is what we call the semi-perimeter. And semi just means half. So it's the half perimeter. Perimeter is the total of the outside. So S is that cut in half. So given your 3 sides, you can find the half perimeter and then put all this stuff in. And you will get your area. All right, so let me show you. Let me show you an example. And we'll go back to that one that had sides that were length 5, 7, and 11. Now, if you want to use that formula from before, the 1/2 AB sine theta, we would have to use law of cosines to find one angle and then go into it. But instead, we can just use Hero's formula. So let's start by finding S. So S is going to be 1/2 5 plus 7 plus 11. All right, so 5 plus 7 is 12, plus 11 is 23. 23 divided by 2 is 11.5. So that's the semi-perimeter. So then to get the area, we just plug all these things into our formula, into Hero's formula. So we're going to get the square root of 11.5 times, now I have to take this S and subtract the 3 sides. So I'm going to get 6.5, 4.5, and 0.5. Again, I don't label my sides, but what I'm doing is I'm just taking each of those sides and subtracting them from the semi-perimeter. So 11.5 minus 5 is 6.5. 11.5 minus 7 is 4.5. 11.5 minus 11 is 1/2. All right, well, again, we're at the stage where we enlist the help of our technology because life's too short to try to do that square root the long way. I'm actually curious. Did you guys know that there is a way to find square roots the long way, like by hand? It's okay if you've never heard of that, because I don't know that anybody younger than me knows about it. And the only reason I know about it is because I was that guy and always asked the questions, and one of my math teachers showed me. Because with technology, you don't need it anymore, right? But yeah, there's a long way of doing square root. But I just used my calculator, and what I got here was that this is around 12.97. I'll round it to the nearest hundred. So the area of this triangle is 12.97 square feet, square meters, square miles, square whatever it is. So Hero's formula, it's kind of a nice little cool one, because it lets you find the area without actually having to do anything but use the side. All right, so there you go. There are a couple of new formulas for you to find area to add to your list. And like I said, you will end up using, especially the AB sine theta one, 1/2 AB sine theta. You'll use that a lot. All right, cool. Well, there you go. We just did trigonometry. I mean, officially, trigonometry was these last 2 days. We now know how to measure anything in a triangle. Yeah, we needed a lot of stuff to get us there, right? But there it is. There is thousands of years of measuring triangles condensed into 2 days. Crazy. And yet trigonometry. All right, so I think we're good for today. We'll go ahead and call it good here. We'll stop here. So what we're going to be doing as we continue forward is just looking at more applications, right? More applications of what's going on. So just FYI, on Monday, there is no class. Monday is Memorial Day. Memorial Day, the college is closed. And so even though we're not physically at the college, we are also going to be closed. Okay, so enjoy that day off. Enjoy doing whatever you happen to be doing on that day. So then the next time we're going to meet is a week from today. So on Wednesday of next week, it'll be June 2nd, I believe. And we'll just keep looking at applications of trigonometry. All right. And so for the next couple of weeks, that's what we're going to be doing. There is no quiz scheduled for next Wednesday since it's a short week. And also the homework sets that are normally due Monday nights at midnight. Since Memorial Day is an off day for us, those have been moved to Wednesday. So your next homework sets are actually due a week from tonight. All right, but those dates are in Canvas, so you can, don't worry, you will be reminded if you keep looking at your Canvas calendar. All right, so I think that's everything I've got for you. Any other questions from you guys here before we call it a day?
Can I ask you a question about the homework real fast?
Absolutely.
Okay, wonderful. It's 9.5 and it's number 8. Oh no,
Okay.
it's chapter, which one is it? It's the chapter 9 review, actually. Sorry about that.
That's okay. Can you actually, because I'm not at my computer, can you just tell me what the question is?
Yeah, so it's cosecant of 4x minus 5 equals 0.
Okay. And we're just solving it?
Right.
Okay.
It got me tripped up, the inverse of cosecant.
All right. I'm going to suggest that we don't think of it as cosecant, but we turn it into one of the big 3.
Okay.
Because you're right, like inverse cosecant, we never talked about it. We don't know anything about it. You don't actually have it as a button on your calculator, most likely. So instead, let's bring it back to its big 3, buddy. So which one is cosecant tied to?
1 over sine.
Okay, so cosecant is going to be 1 over sine of 4x minus 5. So if you're ever just given a cosecant or cotangent or a secant, turn it into the other one by using the reciprocal, because I think it'll be a little bit clearer now. All right, so what would you do next if we had this instead of the cosecant?
I also tried it this way and still, I was thinking multiply sine by both sides.
I think that's awesome.
Okay.
And the idea there is just the algebra trick of getting rid of the fractions, right? Because over here on the left, the sine of 4x minus 5 are gone. So that's just plain old 1. And then what do we get on the other side?
0.
All right, 0 times sine, of course, is 0. So now we're at 1 equals 0.
So undefined.
Okay, and that's when you go, no, 1 does not equal 0. All right, that's not true. Well, anytime we run into something like this, since we know that this is false, what that means is that our equation has no solution. So this actually isn't a bad thing. I know a lot of times when this happens, students go, this is horrible. I don't know what to do. No, it's not horrible. It's actually really good because it tells us everything. Since this is false, that means that there is no solution. There is no number x that will make this thing true.
Got it.
So no solution. If you do this and you end up getting a true statement, like 1 equals 1, then what we know is that everything works and it's actually an identity. But yeah, this one, there's no solution. Never does cosecant equal 0. Never happens. Cosecant is always greater than or equal to 1 or less than or equal to negative.
So in Canvas, do we just simply put no solution?
I don't know.
Okay.
It depends what it's asking because different ones will tell you to do it different ways. Right? Sometimes it will say, type in, if no answer exists, say, type in this phrase or whatever. So I can't answer that without actually looking at the question, but it should be clear from the instructions what to do if there's no solution.
Okay, I'm looking at it now and it says find for the 4 smallest positive solutions. Does that change anything?
No, what else does it say?
I think you should put D and E. I'm not 100%.
I tried D and E, it's not working.
So
Try no solution.
all right. So all right, without me actually having it in front of me, I don't know the answer to that.
Can I share my screen?
Sure.
Okay, sorry, I don't mean to take up your time too much.
No, that's all right. Go ahead.
Can you see it?
Okay. So what you read or what I wrote up here isn't the same as what you got on your screen.
Okay.
Because I had that -5 inside the cosecant. And that changes things greatly. So why don't you go ahead and quit your share real quick
Okay, sorry.
so that I'm a little bit bigger here again. So the -5 is actually outside the cosecant. So for this one, again, we'll go with we'll move that 5 over by adding it like we normally would. And now if we turn this back into a sine, so we have cosecant is 1 over sine. Again, multiply by sine. Those signs cancel over here. So we get 1 is equal to 5 sine of 4x. And this will have solutions. Because if I divide by 5, to get my sine all by itself, now I can do inverse sine. And then this is just like any other problem. It's actually very similar to one of the ones you asked me in office hours the other day.
Right.
Right. So you're going to do inverse sine, but then also check for the other option. the one that's in quadrant 2.
Got it.
Add your 2 pi n's, and then you're gonna have to divide by 4.
Right.
Seek out the 4 smallest ones.
Wonderful. Just getting me to this part is what gets me lost, but thank you for clarifying.
Yeah, you're welcome. So again, when you run into things that are not the big 3, make them the big 3. Turn them into, and then go from there. You should be good. All right. So with that, I gotta run. I got class starting here in 2 minutes. So I will wish you all well. Hey Nick, I just saw your message. I will be there tonight. Pop in whenever. Right. Okay, so everyone have an awesome week, and I'll see you all on Wednesday.